Hello, iNode. Today, here to talk about a little bit of static analysis. It's pretty exciting. I know Morten is fairly frightened of what's going on with static analysis. We have your ritual knife there that you can put yourself out of your misery if you need to. But I think there's some exciting work that's going on, and I'd like to share what that exciting work is and what it can look like for you to use static analysis. First, let's talk a little bit about what static analysis is and sort of how to think about static analysis. So we need to give an ontology for a little bit of what it is.
Well, okay, hold up. We just used some big words there, and I think we need to acknowledge static analysis. This is kind of a computer science-y term. This is an APL crowd. This is a naughty word. This is a naughty word. Okay.
All right.
Maybe we need to reevaluate here. So instead of that, maybe let's start here, assuming nobody has very much computer science knowledge at all, and let's just go from the absolute basics. You guys are APLers here. We're not going to presume any computer science knowledge. So let's start without worrying about that too much. And let's think about what are the things that you might do when running your code isn't enough, right? So there's one place where you always do this, right? Everybody is already doing a form of static analysis for themselves. Can you guess what it is? It's when you look at your code, right? When you're reading your code, you're doing a type of static analysis. And so we're really thinking about this kind of a question. And we can think about reading your code in really two different ways. There's reading your code because you want to check that something is correct, or check that something behaves the way you want, or learn something about your code. And then there's reading your code because you want to change it. Maybe you're doing a migration, maybe you're doing something else. And that's how we're going to frame this going forward.
Well, actually, Aaron,
yes,
we have a tool for this.
Oh, do we?
Yeah, we have tool support, right? That's what we've been working on, right?
Oh.
So before we get into talking about like the full shape of the tool, we want to get you started, give you a feel for what it looks like to use what we have now, what's working right now, and then show a little bit of a vision of the future of where we can go with static analysis and what we have our eyes on. So the overarching sort of driving vision we have here is to make it easy to answer questions about your code. And I want you to kind of think of this. When I ask people about static analysis and what they think it can do for them, a lot of times there's this gap about understanding what static analysis is. So I want you to think of like, if you had a black magic box that could just say answer any questions you had about your code base, that's what we're trying to build that magic box essentially. And so we want to know what questions you could use for that.
Yeah. What kind of questions, I hear you say? Well, fortunately, I've got a list. All right. So, do you have any singletons living in your code that might surprise you later? Do you have any code that depends on certain errors? Does your code handle empty array prototypes? Have you sanitized your data from unverified sources? Have you ensured data security between your client data? Have you hidden any dependencies based on index origin? Do you index any database arrays not using field names? Do you use some old idioms that can be replaced by new primitives that we've created? Do you have any naked strand assignments sitting around? That's Morten's favorite. Are you making any strand assignments vulnerable to being confused for modified assignments? Do you make any dangerous assumptions about your empty arrays being justified? Can you convert functions back and forth between trad funds and defunds safely? Are you passing an operator to a function that unintentionally captures shadowed names in an operator? Ask about magic functions and key. Do I have any strand assignments against vectors that might not be the right size? Do I have any rank or type errors sitting around? Do I have any code whose empty prototype might be the wrong element? Character vectors versus numeric. Is the loop iteration independent? Can I use isolates for this? Can I make it parallel? Is it safe to reorder these statements? Does the function set any locally shadowed bindings, right? Do I have any duplicate names or labels sitting around in my code? Where am I using functions via alias instead of via namespace reference, like fgets namespace.f? Right?
Still going.
Do I have any race conditions between threads? Do I depend on variables that might not exist? Do I have dead or useless code sitting around that's unused, or maybe it's broken and I don't know about it? Are there unused variables in my functions that I've shadowed? Do I have unshadowed variables that really should be shadowed? Do I have any local bindings in defunds that I've actually secretly used beforehand, but I shadowed them later on? Crystal clear, eh? Good?
Oh, hold your questions to the end.
There's subversive elements.
Yeah. So that was a huge blast of questions, and we've seen all these in real code. But let's go looking for how we can find what it looks like to use our current tooling to find those kind of problems in code. So here's just a little example. I know some of you have seen of this recently, but can you point out any problems with this code?
Dialoggers are not allowed to answer this.
Please, like anything. Okay, that's one.
Isn't it mostly problems related to instead of one?
I moved it to index origin 0, thank you very much.
Well, now you confuse the hell out of me. Array classes the namespaces for arrays.
Okay, sure. Any others? All right, let's go through some. So, I'm sorry? Inefficient. All right,
okay.
That's a very good one. We'll get to that. Yeah, it's very, very perceptive. So one, we have magic numbers just in our code. It's if we're playing with code and just trying to play with the problem space and then want to turn that into something production. It would be nice if we don't have to manually inspect this. We can just turn it into a global variable or some configuration parameter. But what if, we mentioned efficiency. What if we want to change having this giant matrix into an inverted table representation? This is a big problem I've heard with some code bases where it's scary if you have this data that you've grown and we have a lot of code working on it. We want to be able to ensure that every place that we're relying on the particular shape data that we can convert that, and we can mechanically or if we need to manually. So there's two of them back. We need to know sometimes, especially during migrations or something, you need to know if some of these primitives, some of the schizophrenic operators are reductions or they're filters, or you need to know if it's a function or an operator, what it's doing. What about query mask itself? What if if you're thinking, okay, we could look up at this expression here, and you could maybe imagine writing a regular expression getting close to something like this, like trying to find it. But what if query mask is some complex expression with parentheses in there? Then it becomes a little bit harder to get a handle on. Or ages even could be something that's complex, right? So we want something that's more robust to be able to get us a handle and say, whenever we're talking to another human, what this code is and what are the salient pieces. We want to be able to say that mechanically in code.
Now, this number 5 here, this is the real meat and potatoes. And number 5, I guarantee you every single APLer has had to encounter this at some point in their life, at some point. And let's consider this by walking through a basic example of this. So let's instantiate database as one of these matrices. We're going to make it 3 rows, 2 columns. Brandon's going to be in there twice. That's fine. We're going to query for Brandon and Aaron, and we're going to extract out the data, and we get 2, 12, 2. OK, not too bad. Let's sum it up. We get 16. That's the basic intent, right? I think everybody that's what we're trying to do at some level, right? So let's change this up. Let's throw Morton into the mix here. Now what do we get? I heard a 0. Any others?
How long is your name again?
Thou hast made a critical fault. Thou hast forgotten types. Thou shalt not forget the prototype. Right? So DB, remember, is a mixed type. Right? So what's the prototype of this thing? Right? What we actually get is this, which is a scalar with the 0 identity elements. That's correct. But it's basing its structure on the prototype of the incoming input. And that is because if we just extract out the empty vector here, the prototype is based off of the first element in the matrix. Right? Now, I noticed that none of you immediately jumped to, oh yeah, there's a problem with that bug somewhere. So chances are, at some point in your life, you've had to find this kind of code just sitting around. And so trying to look for, have I made sure that I accounted for all my empty array cases or my prototype cases can be sort of a challenging thing to look for. So let's go try to find this code and imagine what we would do. So what we can do right now, let's think about what we could do if we were just working with the tools we have available to us right now. And we want to look for instances of this somewhere in our source code. So we could start with the Co-dfns compiler. That provides a parser to us. And the parser, we can take in our code, our source code, and it's going to give us some kind of AST. This is some kind of structure that shows us how our code is laid out, but it does all the parsing for us. It sort of does a lot of that inference. And so if we extract the AST, it's basically an inverted table with a bunch of fields. And we're going to ignore some of those fields, but the fields we care about here are, we're going to get that parent vector, which I've talked about before. It tells you the relationships between the various nodes, elements of your code. And then every piece of your code, like this plus and the slash and the query mask, are all going to have a type. Like it's a variable, it's a function, it's a primitive, something like that, and a kind, and then there might be a name associated with it, like query mask. And if it's a variable, where is that variable defined? And so to look at this, to get some examples of this, if we want to look for some expressions, right, we might say, well, the expressions are the types that are like strands and applications, like monadic application and dyadic application. And that'll get us a Boolean mask of all of the expression nodes that exist somewhere in our code. And we might say, well, I want to look at all of the top-level namespaces that are around. And so roots is saying, well, I want the top-level things. So if my parent is myself, I'm my own parent. And that means you're at the root, because there's nobody above you in the tree. And we might look for dyadic expressions, right? So we want these are expressions, but they're kind 2. So they're dyadic expressions. And we might look for monadic operator expressions. And those are operators. And they have 2 different kinds, because you can pass functions or arrays to them. And we separate out, are you calling this operator with arrays, or are you calling this operator with functions? And we might look for all the places where we define or shadow variables. So our definitions, those are variables that appear inside of our headers. So like our trad funds headers, or that appear in the namespace global binding set or the environment, things like that. And we might say, well, what are namespaces? Well, namespaces, in the Co-dfns parser, we treat namespaces as trad funds that have a special type called 0. So we call them T-naughts or T0 nodes. And what we might do is we might say, well, let's walk for every parent, or for every node, let's go look up the tree and find the nearest namespace that we belong to. So NS is going to tell us for every single node, every single piece of our code, which namespace does it belong into. Right? And so this is what we call a tree walk algorithm. It's an idiom that I've talked about in the past. I won't go into too much detail here, but the way you could read it is, follow my parent until I find a namespace, or keep following my parent while I'm not at a namespace, right? And we can look for all of our primitive functions, so things like plus or slash, those are going to be primitives of type or kind 2. And then our operators, those are primitives, but those are kind 3, so that would be like this reduction over here. And so this sort of forms some basic things we could ask about the tree. But now let's say we actually wanted to find expressions that look like this thing here, right? We're going to need to look up specific names like database. So we're going to have this little utility function that says, is my name equal to this thing, right? And let's instantiate this expression in a slightly larger piece of code. Okay, so this larger piece of code, we've got a database that we're loading in with some kind of loading function. We don't define that. And then we've got this query mask, which is going to look up the emails and reference those on the basis of another database of Dyalog employees, say, or something like that. And then we're going to filter those things out. So how would we go about finding this? It might be difficult if this was buried somewhere to find it using just a regular expression. So we might, to start with, well, let's find out nodes that are actually the database. We want things that are specifically referencing this DB. So this DB we can find with this piece. And the way we look at it is that DB is a definition. So these are our 2 definitions, and we've got this mask defs. And it's in the top level. So these are all the top level statements. We only have 1 namespace, so everything's in the top level. And we want it to be named DB. And so there are only 3 things in here named DB. Put that all together, and there's only 1 thing that matches that right now, which is that assignment, that definition there. And then what we can do is we can look for all the expressions that use DB somewhere. And to start with, we might look for variables, right? These are all the variables that occur inside of our code. And we want those variables to be bound or assigned to DB. It only really gives 3 variables that match that. And then we want it to belong to an expression. So we say our parent is an expression. So we belong to an expression of some sort. And these are the 3 expressions. We put all that together, and there's really 2 places where that appears, right? And so then what we can do is we can do another iteration, and we can grow this mask. So to start with, we just selected these. But what we can do is on each iteration, we can build this mask up and checking, well, this expression, anything that contains that expression is also going to be an expression that contains dB. And so we can grow that out. And at each iteration here, we grow this out further and further until we've selected all of the database expressions, all the expressions that use dB. And in this case, this expression doesn't use dB, but these expressions here do. And so that's our new dBx, or database expressions. And then we can look for all of our indexing expressions. And so here we start with primitive functions named brackets. So those are our indexing locations. And we want those to belong to dyadic expressions. Those are the these little dyadic expressions here. And we put all that together. This whole piece here selects these these three indexing operations. And we want the expressions that are these index operations. So we grab that parent. And when we do that, there are three indexing expressions here that we grab with that statement. And so that tells us where our indexing expressions are. And you'll notice we're getting closer because now we have this indexing expression given here. So if we want the indexing expression that involves dB, we're going to combine these two together. We're going to use dBx and say, well, let's look at all the dBx's and let's find the first part of the indexing piece, because we don't care if dB is used here in this case. We care if dB is used on this first part. And this is, you can read that as the first part of an expression. That's first occurrence for people who aren't familiar with that new. The monadic version of that is, it gives you a first occurrence of everything. And so then we want the parent to be one of these index expressions. So we want a dBx that also has these index expressions. So we're going to grab those out. And once we select all of that, we only get two database expressions. And we want the parents of that, so we want to include everything in there. And so our index expressions that have dB in them are these two things here. And so there are only two of those. The other indexing expression does not involve dB, so we're not going to select that. And then we want to look for reduction operators, because this whole thing is actually an indexing expression that happens to have this reduction operation on the other side. So that's what our redox is going to do. So we're looking for a primitive operator. There's only one in this case here. And we want it to be named reduction. And we want it to belong to a monadic operator. We want it to be used. And so that's where we get this. Selecting that out, that redox selects this reduction. So you see that same pattern that we've used across the whole board. We're looking for a primitive operator named slash that is inside of a monadic operator expression. And so now if we look at that, we have this thing and this other indexing expression. And really we want the expression of both of those combined together. And so if we take our redox here and we think about our index expression here, that is the indexing expression, well, those two share a parent. And so if we take the intersection of the parents of those things, we'll get this expression here, and now we've found what we're looking for. We've done that search, and we found our resulting expression. And we could do this, and one of the things we can do is now that we have a handle on all of those points, we can find them. That's one nice thing. But we could also, if you, Asher's going to talk a little bit about this in his parent tree vector manipulation talk, and he's going to touch on it, I think. But we could take an expression like this, and then we could either automatically or semi-automatically convert it to one of these others and put it back into our source code for ourselves, or print out a list of these and say, hey, we think you should change your code to this. Go check here and go change all these places because we found instances of this. Go fix this here. And that's the kind of thing that we can get from static analysis for this kind of a problem right now, just based on the parser.
So that's cool, Aaron. I mean, we found a reduction operation that is using data that came from some database, right? But the example that you give, I'm going to back up for just a second. This example that you give is kind of basic. I mean, actual code in production is connecting with SQL databases, and it's, you know, Kafka has some Kafka integration, and there's global variables and a lot of state that's that makes the actual expression itself harder to find. It's not immediately obvious.
You got an example?
So we have an example like this, right? Where we have, you know, this is some specific application logic. We're using load and store to maybe read and write from a database or some external data integrations. And then and then we're querying in some different location, and that's somehow feeding through, and we have this Q1 thing that's like this query name, and so it's not as straightforward as the previous example, right? But it's a little bit closer to like what we would expect in production code. But let's show that what we can actually enhance the kind of data that we have. So what Aaron introduced at the beginning, we gave a little DSL to how to say, here's an expression, here's what a trad fun is, here's what a namespace is, and here's how we say it. Well, we can actually enhance that DSL with some application-specific logic, right? And by doing that, we can take this little diff, right? So we can change the previous code that we had. This is what you were just looking at. We can take these 3 lines and change them to something like this, where we have some code here that's embedding application-specific logic to get at the exact same expression that we were trying to get a handle on. So we want to look at this reduction here, and it's getting some database it's over some database data that we're getting up here, right? So first, for example, so what is this database? This application-specific logic would look like. So we could think about every single node, every single expression, and every single primitive, and what the data connection is between them. And so if you did that global across your entire code, it would be this giant graph where every single expression potentially connects to every single expression, and it would be very memory intensive. But we can split that up and say, well, okay, we only care about certain pieces of code, certain, like this database entry point, potentially touching other pieces of our code base. So if you want, or like specific like user data that's potentially dangerous that you need to clean up first, you need to sanitize before you're getting it in and send it to execute or send it to any other potentially dangerous operations. So this would select, so your used parameter would be your sources that you want to worry about. And then uses here tells you what those nodes connect to potentially, the data dependencies between them. And then by combining these 2 together, we can say, oh look, well these 2 expressions here are using our database input, or whatever your input, a Kafka input or anything. And then down here, so our previous 2 lines here just combine. Once we have created used and uses and used, then we can collapse those down to that 1 line. And then down at the bottom line, all we have to change is this. We're doing the same kind of thing. We're saying we have this database, this index expression, and that we want to make sure it's any index expression that is using this database data. And then we need to expand that out to say, well, anything that is kind of being touched by that, and then just shrink that down to, or simplify that down to the reduction expression in any of those expressions that are in our code base. So we've taken any sort of, what we have seen is that there's a fairly simple, straightforward way that you can find. This is like obviously like a security issues or something where you're having tainted data that comes in, and you can find potential, like if you have execute expressions, and find exactly which parts of the code base potentially are executing dangerous code. Right. So the vision is a static analysis tool for APL notation. We have things that are working, and we have things that we are working on. But there's parts that you can get some of this in your code. You can start using this now for special analyses, like the examples that we looked at. We're doing this special analysis, trying to find this particular reduction expression that might have user data coming in. We need to worry about it, or it might have this prototype problems that we need to sanitize out or make sure we're not covering. And then you can also, what's critical here, I think, is the code that we saw can be extracted out into particular rules. So like that bundle of code could be we can name it and put it in a CI pipeline somewhere so that we know we're finding prototype. We're checking every time new code comes in, we're checking for prototypes. And then, of course, security issues that are sort of in the same line. And we want to be able to trace, normally whenever you're looking through it, instead of doing this all by your eyes and with your brains, we want to be able to trace data, all your data flow through your entire application mechanistically. This is something that we can do it. We're doing it. Now, there are limitations, so migration assisted, part of the mechanical, like making mechanical changes, there are certain pieces that are hard to get a handle on, like APL Plus, and whenever coming to Dyalog, there's certain things that can be found with regular expressions, but other sort of semantic differences between primitives and things are hard to figure out where they're salient. So we can, this static analysis, and what we've shown you is that we can actually find these places that you need to look at. And whenever we have all of these checks, we're not trying to say that you have to write all of this code yourself. What we want to say is that we can have a common set of rules. We can have sort of like a standardized rule set that you can use and perform security checks or linting checks or any sort of compliance criteria that you need to meet that are industry standard. You can just make use of those as is. But then you can also have some of these done in-house that are using more customized rules that are not industry standard and you need for particular compliance reasons. Right? So for finding security vulnerabilities or for compliance and code quality analysis, we want to be able to use these tools to support you in your needs, to be able to find the problems in your code and give you artifacts that you can show to auditors, to show to anybody that needs to have assurance that you're performing these analyses on your code. And you can offload that and say, hey, we've done this, we have the static analysis, we've done this code, and here's how we're doing it, why we're doing it, and here's exactly where we have proven that we've done it. Right? It's not just people making claims. So it allows you to sort of offlay your trust onto some artifacts that can be seen. And through that process, we can help you standardize your security habits and meet sort of these compliance and regulatory laws and rules that you need to abide by. And so through that, we're also focusing on integration with other software. So SonarQube, GitGuardian, and Covertity, and all these other sort of analysis tools that you would put in the CI pipeline, we can easily integrate with them. And we've already done some testing and been able to, with SonarQube in particular, where we just use their API and we're sort of agnostic to any integration pipeline that you need for your internal tooling. And the whole goal here is just to make your life easier, right? We want to make sure that you have tools to answer questions about your code base. So internally to this, we want to make it, we have a story here for having, it's easily customizable, integratable, and usable, and easy to deploy into your code base. But also, on the flip side, we want to make sure that these tools are letting you do this for your application, right? So we want to make, having these tools to be able to get a handle on your code so you can customize it, you can integrate it, you can onboard so you can answer some of these meaty questions about your code base to new employees and help them get a deeper understanding of what your code base is through exploration, and then more robust deployment of your application itself. And of course, so you can provide more confidence in your business practices. Thank you very much. Should we go in the back here?
I think.
Yes.
Okay. You had mentioned that you could set up custom rules, not just industry standard rules.
Exactly, yes.
How would you get a rule that said, if you see a tacit function, rewrite it so it has explicit arguments?
Okay.
That can be done. Yeah, that's one of the easier ones. Yeah.
So there's a frontier here, right, where you can't take any code and mechanically turn it into any other code. But for a lot of the actual tacit function in practice, they're fairly easy to mechanically translate. There are
Tacit.org.
Yeah.
Right. Exactly.
Is there an API for tacit.org?
Well, we can also take the code from tacit.org, and what you can do is you can recognize the tacit function, feed it into tacit.org, and then as part of your build pipeline, your deployment, you can say, hey, we found this tacit function. Tacit.org thinks you should rewrite it as this. We suggest rewriting it. Here's a patch or a PR that does that for you, or something like that. And that would go into your system.
But it's harder to get rid of forks.
Forks also, we can recognize forks, and so you could scan your entire application to say, get rid of all the forks and replace them, and if tacit.org falls over at it,
and I can
send it to me
in
and
magic LLM that's trying to be
If you
You
wanted
could,
to,
you
yeah,
could,
you
you could.
could totally do that. Yeah.
I mean, so that API that we gave you at the beginning, there would just be a single expression that you could say, that would say tacit trains.
Those first 4 pages of, do I have this, that, the other? I want an LLM to write that.
Yeah. I think, did you have,
We had other
or I think we had a
questions.
question with
Let's go
Jay,
in the back here. We haven't heard from you before.
Okay.
Yes. So among other things, let me just confirm before I ask my question. This tool can do like ahead of time static type inference type stuff.
Yes. It doesn't.
Modulo the halting problem.
Right.
That was kind of my question.
Right.
I found that interesting coming from you.
Yeah. Yes.
Usually like vehemently against any type of like type system
Yes.
in
Yes.
APL, and I'm
Yes.
like, a lot of the problems that this external tool fixes would also just be internally fixed from any type of static type inference built into the language.
Yeah.
So is this just making up for the part that?
So this would be a mechanism by which you can get type inference into the system without requiring static type annotations. And the type annotations are the thing that I object to the most strongly.
I don't know why you think static type annotations are required for type inference.
I don't, but we'll talk about that offline.
I mean, you have to have some initial set of static type declarations. Right.
Also see Bernecki's Apex compiler. He did some type inference type stuff already.
Let's get some other questions. We have one way.
Yeah, we
we
need
have
to-
Bernanke in the back.
Yeah, I think
Yes.
we've got a lot of questions here.
We have a lot of questions here.
You had index expression, thingy moves of semicolon 1.
Yes.
And so you're committing a cardinal sin here, for those people who are still religious. Cardinal sin.
Okay.
Never use constants in your code.
Yes,
Yeah.
that was one of the these magic numbers points that we pulled out.
But then you said, okay, now I'm going to change this to ages, and somewhere I've defined that ages is
Sure. Yes.
one column in this database. And that works fine until some bright light says, oh, looky, then the phone number is right here next to the age. So I'm going to use ages plus 0, 1.
Yeah.
Yes.
And, so
That would be a good linting rule.
Exactly. So what we're envisioning here is these exact questions that you have, you could put inside of a CI pipeline and catch them as your code is checked in.
yeah, okay.
And so you can enforce through that mechanism.
Okay, and of course, and then Aaron had another one. This thing, it wasn't typed. You've done the right thing with type. You say this is, it's not type 2, it's type integer or type something. And then, but there was another thing you were talking about, and you were giving integer names to them,
Yes.
which is you're in the same problem. And the reason I find this interesting, aside from finding other people's bad code, is I want to write a compiler, and I don't know what to call it. This thing is.
I mean that's what this is. This is backed by a compiler, right? So there's definitely a lot of overlap between yours and what we're going on, what we're working on here.
Yeah.
So,
Yeah, but we might want to take that discussion offline.
Yes.
2 minutes.
Yeah.
2 minutes.
Yeah.
Okay.
Let's.
Can we have? I want to hear from people we haven't heard from
Okay,
yet.
okay.
So.
Big question, but quickly, based on the implementation, the compiler, and so on, how far would it be to then jump to formal methods or have something like that?
So I've already experimented a little bit with that. If you see my LambdaConf talk on my favorite verbose programming technique, one of the things that I do is I write up state machines in a certain fashion in APL, specifically with the idea that a static analyzer can take that and extract the state model out and then put that into a formal reasoning system like TLA Plus to let you then do formal reasoning about, say, your network communication protocols and ensure lack of race conditions or something like that. So it's something that's very interesting to us, but the details I think also are beyond the scope of.
One more.
Does
Yeah,
it use the ask for that, or?
Does it
Yes,
use the what? The
well,
AST? Yeah, it would use
we
the
would
AST for that.
I mean, I think one key insight for this is that by using these rules and this language to describe your code base or get handle on your code, you can reduce the information down. You can make summaries, formal summaries, and then we're envisioning that you could use those summaries and have formal proofs, perform formal proofs over those.
Okay.
So that's the general argument here.
A couple observations. Are you thinking about integrating this into as a hook into linked so that we can proactively check code as we're just
Like into link? You said link?
Link, yeah.
Yeah.
That is a great suggestion. We haven't thought broadly about all of the possible integrations.
But I'd like to have this working as I'm writing
in the interpreter.
Yeah, I think
before I put it in there and worry about looking on the back.
I think there are some pre and post processing hooks that Link already has available that you could probably feed this into.
Honestly, I'm not very worried about that. I think it should be fairly easy because other integrations that we've tried have been trivial.
The other observation is how are you developing the rule space? And I'm thinking that, gee, if you could be watching all the mistakes I'm making,
Yeah.
and, I keep making the same mistakes, or the things I have to fix become, reported potential things you might want to include in your data.
Yeah, and if you've got a list of those, send them to us.
Yes, exactly.
You want something more dynamic where it's actually, I agree to do this and I'm sending this stuff to you. So you're just building a database.
Exactly. I would imagine there's public databases on like Sonar.
We're running out of
here.
time, unfortunately. But
please.
let's
get to you
go.
later.
Let's take it offline. We can talk because we've got
Thank you.
People are hungry.
Have lunch.